Okay, now we have 9.1. I'm sorry that chapter 8 was a little bit scuffed. And I'm also sorry that I haven't done these for so long. I think it's been 3 months since I posted my previous 8.5 video. However, we will continue on with integrated math 3. So I'm gonna start. We want to derive some identities, and what identities are basically just whenever you say that something is equal to something, that's an identity. This is an identity right here. This is also an identity because they're equal to each other. So when something's equal to something, it's an identity. We have co-function identities. Now if you recall on the sine, cosine, and tangent stuff, we have sine, we have cosine, we have tan, we have cotangent, so cotan, I'm just going to put cotan even though it's cot, and then I have sec, and then cosec, right? We have sine, cosine, tangent, cotangent, secant, and so cosecant. So each of these, sine, tan, and sec, has their own, they have their own like reciprocal identity, right? This is for example 1 over tan. This is for example 1 over cosine, and this is 1 over sine, right? So these have their own reciprocal identities, but they're also related to the original functions in some way. So sec and cosec are related in some way, tan and cotan is related in some ways, and sine and cosine are related in some way. So we have theta 2 in terms of theta 1. Let's just say this is A, this is B, and this is C, right? So what's theta 2 in terms of theta 1? We have 180 degrees in the whole thing. So theta 2 and theta 1 is 180 minus the 90, right? Because this is the 90. And then we have theta 2 in terms of theta 1. So theta 2 is equal to 180 minus 90, and then minus the theta 1. So you have the theta 2 left, right? This is the theta 2 in terms of theta 1, which is equal to, you simplify it, it's just 90 minus theta 1. Or 90 can also be expressed as, 90 is equal to, it can also be expressed as the pi over 2 radians, because whenever you take 90 and then you multiply that by pi over 180, you will get pi over 2 radians. Pi over 2 radians. So pi over 2 minus theta 1 or 90 degrees minus theta 1, or they're both valid, but we want to take the pi over 2 because it looks nicer whenever we're trying to work on graphs, right? So find all non-trigonometric functions this time of the theta 1. So theta 1 non-trigonometric functions is sine of theta 1 is opposite over hypotenuse. So sine of theta 1 is b over c. Tan of theta 1 is opposite over adjacent. I'm sorry if there's like bag rumbling sound. Tan of theta 1 is opposite over adjacent, so that's opposite over adjacent. That's b over a. And sec of theta 1. Sec is 1 over cosine. If you don't remember the identity, it's 1 over cosine. And cosine is cosine of theta 1 is adjacent over hypotenuse, a over c. So it's c over a, right? So 1 over a over c, that's equal to c over a. Now we're going to find the co-trigonometric functions of theta 2. So we have cosine of theta 2, which is adjacent over hypotenuse, b over c. And we have cotangent of theta 2, which is opposite of tangent, so 1 over tan of theta 2. Theta 2 tan, tan of theta 2 is opposite over adjacent, a over b, so it's 1 over a over b, which is b over a. And then we have cosecant. So CSC, right? CSC of theta 2, which is 1 over the cosine, 1 over the sine of theta 2, and sine of theta 2 is a over c, because that's opposite over hypotenuse, right? Remember your SOHCAHTOA. Remember your SOHCAHTOA, and that is equal to, no, that's 1 over a over c, so that's equal to c over a. Now you might realize something fishy right here, right here, right here, and right here. They're all the same. So the first identity you can come up with is that the sine of theta 1 is equal to the cosine of theta 2. The tan of theta 1 is equal to the cotan of theta 2. And the sec of theta 1 is equal to the cosec, or CSC, of theta 2. Very, very cool identity. You just figure that out just by looking. You can just figure that out just by looking at the results of the trigonometric function exploration. Or you can substitute. Now we're going to substitute this theta 2 for the theta 1. So you'll have sine of theta 1 is equal to cosine of pi over 2, or 90 degrees, minus theta 1. Same thing, tan of theta 1 is equal to cotan of pi over 2 minus theta 1. And sec of theta 1 is equal to cosecant of pi over 2 minus theta 1. And those are your identities. Those are your co-function identities. That's what they're called. I spent too much time on this slide. Next slide. We have another type of identity, which is the negative identity. So what if the angle was negative in the function? I have this circle right here, and if you remember, this is called the unit circle, or the circle. It's just a circle, right? I didn't say that it's a unit circle yet, but I could say that it's a unit circle just by putting the 1 right there. So what's the cosine of negative theta? If the angle was negative, what is the action that's done on it if the angle is negative, like this? Well, if you go way farther, way back in the day, you can see that, for example, if we do that a function like log of x, and we put the negative in there, all the values are reflected on y, reflected on the y-axis. So basically, if we take this cosine of minus theta, all the values are going to be reflected on the y-axis. This is the x value of the function right here. So if we have this right here, it will be x comma y, and that will be cosine theta over sine theta. If you don't know what I'm talking about, go back to the unit circle or go to the pre-calculus review. I have the sorry if the dog's barking, but I have the explanation for this. It's pretty neat. So x comma y is cosine theta comma sine theta. When you take cosine theta right here and you reflect it on y like this, what happens? It goes like this, right? So the triangle kind of like reflects on y. Everything reflects on y whenever you have it negative, which will give you cosine theta minus sine theta, right? Because the y coordinate is reflected, but the x stays the same. So we can actually conclude right now that cosine negative theta is just cosine theta, and then the sine of negative theta is negative sine of theta. And if you recall these function rules, this is evenness and this is oddness. So this function is even and this function is odd. Since tan is even over odd, tan is sine over cosine. Odd over even, it's neither even nor odd, right? But tan has something that is very interesting because we have these type of identities. So cosine over sine, tan is sine over cosine. If you don't remember that identity, tan is sine over cosine. I think I proved it I think I told you it, but if I haven't told you it yet, tan is equal to sine over cosine because it's x over y, x over r over y over r, and then or y over r over x over r, and then this y over x. I explained it better in the unit circle explanation. I also explained it better in the pre-calculus review and the 8.3. I think that was the unit circle video. So tan sine of minus theta, cosine of minus theta. Once we have all of this, we can just put minus outside on the sine, minus sine theta over, and then cosine of minus theta doesn't change, so it's just cosine theta, and then this is going to be minus sine theta over cosine theta, which is equal to, actually I'm a little bit hesitant to call this a neither, but it is an odd over an even, so it probably is, but we have minus tan theta, and that is the answer. So minus tan minus theta is minus tan theta. So those are the three functions you need to know. If you do the cosecant, secant, and cotangent, it's just a reciprocal, so it'll be negative just like the regular functions, right? Next, we have other identities. The sine squared x plus cosine squared x is equal to 1. I'm going to draw this unit circle again. And if you remember why this thing exists, this exists because sine is the x, and cosine, no, I mean cosine is the x, so cosine, and sine is the y. And whenever you do this and you have a right angle, you can use something called the Pythagorean theorem or Pythagoras' theorem, and then you have x squared plus y squared is equal to 1 squared. 1 squared is just 1, and cosine is cosine, x is cosine, so it's cosine squared x, and then this is sine squared x. So cosine squared x plus sine squared x equals 1. We can derive different identities from this. First of all, we have these two special numbers. If we divide by 1 on both sides, nothing's just going to happen. If we subtract cosine 2x on both sides, cosine squared x on both sides, we can get sine squared x is equal to 1 minus cosine squared x. So anytime you see a cosine squared x, you can substitute it with 1 minus the other, 1 minus the co-function, right? So sine squared x equal 1 minus cosine squared x. Cosine squared x equals 1 minus sine squared x. You can also divide, and I'm gonna divide right now. So we're gonna divide by sine squared x on both sides. Sine squared x plus cosine squared x equal 1. So divide everything by sine squared x. This will get you 1 plus cosine squared x over sine squared x equal 1 over sine squared x. We know this function. We know what this function is. 1 over sine x is the cosecant of x. So and they're squared, so we can just put 1 squared over sine squared x, which is cosecant squared of x. Cosine squared x over sine squared x is a little bit harder. Tan is sine over cosine. And I already told you that there's a function that's 1 over tan, and the function's cotangent. 1 over tan is 1 over sine over cosine, which is cosine over sine. So this is cosine over sine squared, which is cotangent squared. So this is one of the identities as well. 1 plus the cotangent of x is equal to the cosecant of x. And what's the other? The other is dividing by the cosine squared of x, which makes that 1, and then this becomes sine squared x over cosine. I'll put it right here. Sine squared x over cosine squared x plus 1 equal 1 over cosine squared x. 1 over cosine squared x is easy, that's sec squared x. Sine over cosine, you already know that, and it's all squared, so it's tan squared x. And those are the identities. So sine squared x plus cosine squared x is 1. Tan squared x plus 1 is sec squared x. And 1 plus cotangent squared x is CSC squared x. Those are the three identities. And I still don't remember them. I still have to do this in order to derive them. It's quite crazy. The amount of trigonometry you have to remember. So we're just going to simplify these functions now using what we know about the functions. right here. This is literally what we've just been doing. This 1 plus tan squared x, is 1 plus tan squared theta. So we have tan squared x plus 1 is sec squared x. So 1 plus tan squared theta is sec squared theta. And you learn to get good at this quick. So cosine theta times sec squared theta is, well, this is 1 over cosine squared theta. And then you have cosine theta, you have cosine to the 1 power theta. So you can remove one of these, you'll be left with 1 over cosine theta, which is equal to sec of theta. So you end up with just this from this, right? You end up with just this from this. This sine pi over 2 minus theta. Let's go all the way from the beginning to get that. Sine pi over 2 minus theta. So this is true, right? But since they're co-functions of each other, you can also do it the other way and it would be true as well. So we have sine pi over 2 minus theta is equal to cosine theta. And then cosine theta multiplied by the sec theta, it's just going to result in this. It's going to result in this. So that's equal to cosine theta times 1 minus 1 over cosine theta, which is just 1. Right? Because cosine theta and divide by cosine theta, that's just going to be 1. Now this is a little harder. We're going to do cosine squared x tan squared of minus x minus 1 over cosine squared x. This is a little harder. We're going to first, I'm going to separate. So we'll have this as a fraction and this as a fraction. Right? Because when I separate, now what I can do is do this. And then I can do tan squared of minus x is equal to tan squared of minus x minus 1 over cosine squared x. Now I'm going to leave it at cosine squared x because everything can be expressed in terms of the sines and cosines. Everything can be expressed in terms of just sine, but we're just going to use sines and cosines just to make it simple, but not too simple. Now notice that tan of minus x is minus tan of x, right, from our negative examples, but this is tan of minus x squared. So since if it's an odd function, you move the minus outside, but if you take the minus outside and you square it, you'll just get that. You'll just get tan of x squared, right? That's just what you're gonna get. Tan of x squared. So if you take this tan of x squared right here, and then you take tan of x squared, tan squared x. So it's just regular tan squared x minus 1 over cosine squared x. You make it nice, sine squared x over cosine squared x minus 1 over cosine squared x. You will get sine squared x minus 1 over cosine squared x. And then I'd say that this is a good enough answer, but if you want to be even better, you can just absolutely amazingly simplify it, and you'd get, this is minus 1 minus sine squared x over cosine squared x. And you know what 1 minus minus sine squared x is from the other question. Hopefully you'll get cosine squared x over cosine squared x, and this will get you minus 1. And that's it. This whole ordeal is just equal to minus 1. Right? It sounds crazy. It's just equal to minus 1. So we got to now verify that these are true. So we're just going to use our algebra skills to verify that these are true. Let's do it. We have to modify. We're only allowed to modify one side of the equation. So if you want to modify this side, you have to modify this side only. This side only. So we have 1 plus cos x over sine x plus sine x over 1 plus cos x. We want to put it in the common denominator. That's what you've been learning for a long time. A common denominator is needed in order for you to combine fractions with an addition. So we have to add 1 over cosine x both sides like this. And no, not add, I mean multiply. Multiply by sine x over sine x. And this is totally allowed because you will get a 1 whenever you multiply it. This will give you 1 plus cosine x squared plus sine squared x over both over 1 plus cosine x times sine x, right? But you can actually do this because they're under the same denominator now. So this we're gonna expand. We're gonna do some pretty messy stuff. This is 1 plus 2 cosine x. If you FOIL this, you'll get this 1 plus 2 cosine x plus cosine x squared over sine squared x like this. And if you see on the identity, if you see there's the Pythagorean identity right here, and this will get you 1, right? This will get you 1 because of the Pythagoras theorem. We have 1 plus 2 cosine x plus 1 over sine x times 1 plus cosine x, which will give you 2 plus 2 cosine x, which is equal over sine x times 1 plus cosine x, which is equal to 1 plus cosine x over, I'm sorry about the noise, I'm going to get to you guys later after this problem. So you have both of these, you can cancel them. You'll have 2 over sine x, which is equal to 2 CSC of x, and that is how you manipulate a function. So we have our second problem right here, 2 cosine theta minus sec of minus theta. Now this sec of minus theta right here is actually technically sec of theta because sec is 1 over cosine, and 1 over cosine is the cosine of minus theta is just the cosine of theta, because we've already seen last time that that's the case. So it's just regular sec of theta. So what you can do is you can actually combine these. So before I actually write the whole expression down, I'm just going to combine these first. So 2 cosine of theta minus 1 over cosine of theta. So we can multiply cosine of theta over cosine of theta right here, which will get you 2 cosine squared of theta minus 1 is equal to this cosine of theta, right? Cosine of theta, and then over 1 minus, and then I'm going to take this tan squared of theta right here, and I'm going to put it in terms of sines and cosines as well. Sine squared of theta. This might look like a mess, and it probably does. It looks like a mess, but it'll work. It will work as soon as we have enough things to prove that it'll work. As soon as we decompose them all into cosine squared and sine squared and sine and cosine, and then we build it back to the functions. But this one only has cosine in it, so we don't even have to build it back. So this would be cosine squared theta. Oh god, I'm sorry about the lag. Cosine squared theta over cosine squared theta. If you can actually do this before I finish lagging. Right, cosine squared theta over cosine squared theta multiplied by minus sine squared theta over cosine. So this will get you cosine minus sine over cosine squared, right? This is cosine squared theta minus sine squared theta is equal to over cosine squared. So first of all, what you can do is you can remove one of the cosines immediately. Those are removed, and then you'll have cosine. You just have 1 cosine of theta over here. Oh my god, it's lagging so badly. It's not even funny how badly it's lagging. Okay, it's not even working anymore. Okay, I'll need to wait then. Because this cannot, it doesn't work. Okay, there you go. Okay, now I can actually make it to work. So this will be cosine of x only at the bottom, which will make our final function as 2 cosine squared. Oh my god, 2 cosine squared of theta 2 cosine squared of theta minus 1 multiplied by cosine of theta is equal to, no, over cosine squared of theta minus sine squared of theta, and nothing works. Cosine squared of theta minus sine squared of theta, and that's equal to the cosine of theta. So what you can do now is you can distribute the cosine of theta into cosine to the third power theta and sine to the third power theta, or you can do something a little bit more smart, and you can take the sine squared of theta right here and make everything into the cosine. So first of all, I'm gonna erase this other problem that I have going on right here that looks way nicer because this software doesn't want to be moved. Please speed this video up 1.5 times because this I'm not going to be editing this, and this stuff happens whenever you do anything. So there you go. Now we have we're gonna turn this. Okay, so it will be 2 cosine of squared theta minus 1, and all of this is multiplied by cosine of theta and divided by cosine of theta and divided by cosine squared of theta, but we're minusing the sine squared of theta, which is 1 minus cosine squared of theta. So this ends up being minus minus, that's 2 cosine squared of theta minus 1, because minus 1, 2 cosine. So this crosses over and this crosses. This leaves the cosine theta alone, and now we have cosine theta is equal to cosine theta, and that is the answer. That right there. That took a lot of trial and error. That took a lot of time because of the dumb whiteboard active inspire crap. But we can go on to the next question, which I think there's one more, and active inspire doesn't want to work again. So we will. There you go. So we're not going to do B and C. This is called Snell's law, and it's basically the sine of this is equal to the sine of this, but this is our function right now. So let's see if we can figure out what it's trying to ask. So cotangent squared of theta 1. What's cotangent squared of theta 1? We want to simplify this this equation, right? So cotangent squared of theta 1 plus 1. So what you can do is you can take one of these Pythagorean identity graphs and right here, I think, yep, 1 plus cotangent squared of x, which will just give you the cosecant squared of theta 1, right? So this is just equal to cosecant. So it's basically n1 over cosecant squared of theta 1. Please work. Nope, it doesn't want to work again. N1 over cosecant squared theta 1, and this is under square root, and this is also equal to n2 over cosecant squared of theta 2. And you can take this and the cosecant, and you can take the square root and the squared, remove them. Now you'll have n1 over cosecant theta 1. And this is the answer, n2 over cosecant theta 2. This could be the answer, but if you want to be even nicer, you can take the cosecant and make it sine. So this is 1 over sine, which will make it n1 sine theta 1 equal n2 sine theta 2. And that is Snell's law right there. That's going to be it for today's episode. I need to do something, and I'll see you next time for 9.2, which is sum and difference of identities. Sum and difference of